Hi, I'm Dr. Kim Klube, Publishing Manager for the Royal Astronomical Society's journals. Welcome to our celebration of 100 years of publishing geophysics. This started off in 1922 with a single paper, and now we publish around 600 papers a year in our journal, Geophysical Journal International, papers by scientists from all over the world. I hope you enjoy these stories we have to tell. In today's story, we share a pivotal moment in geophysics.
I'm Dr. Sue Bowler, and I edit the membership magazine of the Royal Astronomical Society, getting contributions from fellows in astronomy, but especially in geophysics. We've talked about how geophysics began 100 years ago and how that beginning was recognized by the Royal Astronomical Society. But geophysics now is a much broader and a much more data-driven science. We now have much more sophisticated ways of recording earthquakes. We have better seismometers. We even have arrays of seismometers stretching over whole continents. We have more precise magnetic measurements, which help us understand how the Earth's magnetic field varies today and has varied in the past. We have measurements of the heat escaping from the Earth. We have imaging techniques that can show us the interior of our planet in great detail. We can show where there is movement deep beneath the surface, in our core and in the rocky mantle above it. And we think about how that magnetic field stretches out into space, how it interacts with the sun's magnetic field. And with some current space missions, we're also looking at the interior of other planets, such as Mars. This changed largely as a result of wartime efforts, particularly in submarine warfare, first in World War II and then in the Cold War. In World War II, the technique of sonar, that's using sound waves sent through the water to bounce off either the ocean floor or a submarine. The time that the echoes took to come back to you tells you how far away the ocean floor or some submarine in the way is from the source of the sonar. And it was soon realized that if you really want to be accurate about this, it helps if you have a map of the shape of the ocean floor. So that started to be developed. Come the Cold War and the invention of a magnetometer to measure the magnetic field, submarines were also tracked because of the effects they had on the Earth's magnetic field. But once again, it really helps if you want to find a metal submarine in the deep ocean, if you know what the magnetic pattern recorded in the rocks beneath is. So during the 40s, 50s, and early 60s, there was a flurry of mapping of the ocean floor. And then it wasn't just the military, it was also research institutes, largely in the United States, but also in the United Kingdom. The geophysical data coming through in the 50s and early 60s showed some surprises. There was a line of mountains running through the middle of the world's great ocean basins. This is what we now call the mid-ocean ridge. And with the magnetic data that came later, there were patterns of magnetic stripes that ran parallel to those ridges and symmetrically about them. This got the geophysicists thinking. And one of the things that they thought about, and a few people published in the early 60s, was the idea that the ocean floor forms along those mid-ocean ridges. They're made of volcanic mountains. So you would have volcanic eruptions forming the rocks of the mid-ocean floor, which cooled and moved away to each side as if carried on a conveyor belt. This was considered an outlandish idea at the start, but as better geomagnetic data was discovered and mapped, people came to realize that this was where the ocean floors formed. Well, everything changed in the 1960s because all of a sudden there was a whole lot of data, geophysical data, about the ocean floors. The idea of continental drift wasn't new. Ever since people had started publishing reasonably accurate maps, the coincidence, or was it, of the similarity of shape between Eastern South America and Western Africa had tantalized a lot of people, not least Alfred Wegener, a German meteorologist in the early part of the 20th century. He put forward a very established theory of continental drift with lots and lots of evidence, not all of it, unfortunately, good evidence. One of the reasons nobody really took these ideas seriously at that time was because there was no mechanism proposed. Now, this was a time when geophysicists, such as Harold Jeffreys, for example, were using seismology to try and understand the nature of the interior of the Earth. And what their studies told them was that there was no way the continents could plow through the solid rock of the ocean floor and move about in the way that was suggested by continental drift. Plate tectonics is the modern, accepted, very well tested theory of the surface of the Earth, in fact. It's based on the distribution of earthquakes and volcanoes across our planet, and says in essence that the surface of the Earth is made up of about a dozen rigid regions that move relative to each other. These regions where there are very few earthquakes, not many volcanoes, are called the plates. And the plate boundaries are where each rigid region moves with respect to the other one. That's where the earthquakes are, and that's where the volcanoes are. And as a result of this movement, the oceans change shape and the continents move across the Earth. And what I find most fascinating about this particular theory is that it was only developed in the 1960s, just over half a century ago. It's not the whole story. To understand exactly what went on in the 60s, you have to actually go back to 1922 and the first issue of the Geophysical supplement. The first paper was published by Herbert Hall Turner, who was an astronomer and seismologist who really pushed to establish independent publishing of geophysical results by the Royal Astronomical Society. And that first paper by Turner was, it's a very clever paper. He takes the existing model that most geophysicists at the time were working under, which was that earthquakes are a shallow phenomenon. They happen underground, but not very far underground. And he tests it, as we do with all theories. Now, Turner was a mathematician, and he looked at the predictions that were made about the location of an earthquake. So you start with seismological stations, and you look at when the vibrations from an earthquake reach stations all around the world. And then you can infer from the locations that first feel the vibrations from that earthquake, you can infer that the earthquake was nearer to them and further from other stations. So Turner took a hard look at the data And he discovered that for some earthquakes, this model didn't quite fit. And it didn't fit at the seismic stations that were on the other side of the world to the most probable source. And he worked out, in fact, that the problem was that some earthquakes were very deep. He had them at 250 miles down in the earth, which was very surprising at the time. But it is in fact the existence of those deep earthquakes that allowed geophysicists in the 1960s to understand what was happening in the global pattern of plate tectonics. Yes, better seismometers made a huge difference to how well geophysicists could locate the sources of earthquakes and delineate plate boundaries in the oceans that way. But there were improvements in all the ways of collecting geophysical data as geophysicists worked with this new framework of plate tectonics. It was incredibly powerful. There's one paper, a very long paper, nearly 100 pages, in Geophysical Journal International in 1971, that sets out the whole history of continental movements, with India and Australia moving away from Antarctica, and India driving into Asia and forming the Himalayan mountain belt. And it's all there in that one paper, and it all comes from data locked up in the rocks of the floor of the Indian Ocean. It's a real achievement. And what we've learnt, if you like, since the 1960s is that this theory, plate tectonics, works beautifully in the ocean basins. It's a little bit simpler there. But when you look at the whole pattern of earthquakes and volcanism and deformation on land, on the continents, it's a lot more complicated. And that's something that geophysicists are now able to track with continuous monitoring of earthquakes, broadband seismometers, all sorts of new technology, because it's very important what happens in earthquakes on land, because that's where people live. So geophysics now has quite a strong emphasis, as well as on the continuing research on the interior of our planet, but actually on solving problems that matter to people. This is a modern map of the plates making up the surface of the Earth. You can see a plate boundary down the middle of the Atlantic Ocean. This is the mid-Atlantic ridge. It's a mid-ocean ridge, and the little red arrows show you that the plates are moving apart and new ocean floor is being generated all along that line. So the South American plate and the African plate are moving apart, carrying their continents with them. If you then look on the western side of South America, you can see that you have the Nazca plate next to the South American plate. And the red arrows that show the relative movement of those plates are moving towards each other. This tells us that this is a subduction zone. And the Nazca plate is sliding beneath South America, making that part of the world at risk from earthquakes and notable for its volcanoes. If you move a little bit further north to the west coast of the United States of America, you can see that the Pacific plate is moving relative to the North American plate. And the red arrows there show that the movement is parallel to the plate boundary. This tells us it's a strike-slip plate boundary. And we know from the history of earthquakes in California that this is a place where there are significant earthquakes that affect people on land. What's changed in the last 100 years isn't the curiosity, it isn't the concept of thinking about planet Earth. What's changed is the sophistication of the tools we have to collect geophysical data and observations, and the ways in which we think about them and manipulate them and develop scientific understanding of them. And that's largely as a result of publishing about geophysics, sharing ideas, testing ideas, bringing data together. GJI has been doing that for 100 years. It's still doing it now. If you want to have a look at what's happening in geophysics, have a look at GJI. And here's to it carrying on doing that for the foreseeable future.